Okay, so hopefully everybody had a good weekend and break on Monday. So just a little bit of review from last class, just to kind of get us back into the mode we were going from. So last week we talked about a lot of number conversion stuff, just so we understand that there are different ways of representing numeric values, different languages we can use to represent numeric values. We choose decimal because we have 10 fingers, 10 toes, but we choose binary for computers because they like on and off. And then we had two other bases, octal and hexadecimal, that also were popular in computers. And we saw that the reason for that is that shortcut where we can represent the entire collection of octets, the entire collection of base 8 values, octets, 0 through 7, using 3 bits. And we can create the entire vocabulary of hextets for hexadecimal, 0 through 9, A through F, using 4 bits. And we discussed that at some point in the future, if we were to need to go to a larger value to represent larger memory addresses, whatever it is, if the next step would not be base 17, the next step would be base 32, which would allow us to represent all of the vocabulary of that language, 0 to 31, the alphabet leading 0 to 9, and A through wherever it is, would be fully represented in 5 bits. Make sense? We can go to then to 64. Now you're fully representing in 6 bits, although now we've run out of alphabet and we got to start moving over to Klingon or something like that. Probably something we aren't going to, well, certainly something we're not going to run into in your lifetime, and maybe something we'll never run into, because with quantum computing, eventually we might have to look at other ways of representing things. So we have some runway for now. But the appreciation we want to have for numbers, as we really try to understand this computer that we're going to be trying to tell what to do, is computers don't just use numbers for math. They also use it to represent, to index things. You know, we talked about the ASCII character set and the Unicode character set, where Unicode is a superset of ASCII. The first 256 characters of Unicode represents the 256 characters of the ASCII character set. You know, and this is the characters for all sorts of languages around the planet. And us having, since computers like numbers, us having a numeric index for a particular character. So there's a lookup mapping. That makes sense? So at the very least, we know of 2 uses for numbers. We can do mathy stuff with them, so representing magnitude, and we can also use it to uniquely index stuff. All right, so right off the bat, we see 2 uses. So at the very least, we can just say numbers aren't always for math. Okay. And we recognize that we represent numeric values in some different formats, because computers like binary, we like decimal, and then there's some convenient translations in the middle, which is why we chose those certain bases. Make sense? Now, from a modern day computer scientist perspective, you're not going to have to deal with binary or octal or hexadecimal that often. If any of them, if you see any of them very often, it's going to be hexadecimal, and it's going to be more of, you will see it, not necessarily that you have to process it, but you'll see it by way of a memory address. And we'll definitely this week see that example. But whenever you see memory addresses in computers, we use those numbers to index locations inside of your computer's memory. And last week we talked about how a human being's version of addresses, you know, like your address of your house, 123 Elm Street, blah, 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 you know, Grafton, Wisconsin, 53024, whatever it is. That's a very complex address that we use to represent our location in the world, right? Where computers, even though they're scary looking, have very simple addresses. All the places are on one big long street, and we just say that's house 0, house 1, house 2, house 9, house A, B, C, D, because we're counting in hex. Make sense? And why might we be counting in hex? because that street is really, really, really long because we've come up with ways of storing a lot of stuff. Your modern computers probably have a minimum of 8 gigabytes of RAM in them. Most of your computers probably have 16, some have 32. Anybody have more than 32 gigs of RAM in your computer? In your either your gaming machine or your laptop, how many of you have at least 16 gigabytes of RAM? I would think most of you. Okay, if you don't know how much RAM's in your computer, that's your homework for next class, is make sure you're aware of the technology that's around you, because we're computer scientists, or at least in a closely related field. Who's calling me? Okay, so that's something you should probably know. Anybody know if you have at least 32 gigabytes of RAM in your computer? Most of you gamers probably would. Anybody have at least 64? Okay, we got a maybe. That's actually more concerning. If we maybe have 64, then did you build your own machine? Or did you buy like a gaming computer? So we're talking about memory, not hard drive space. So this particular computer here has 96 gigs of RAM in it. Now, why would you ever need that much RAM in a computer? Do you think I very often use 96 gigs of RAM? Up here, it's telling me how much RAM is available. I have just about 60 gigs of available RAM. But quite commonly on this computer, I run the Mac OS, I run Windows, and I run Linux all simultaneously in virtual machines. And each of those virtual machines takes up system resources. So you need multiple cores in your processor. So this guy has a M2 Max processor in it, which has, call it 128 cores logical. But I can divide that up into Windows gets some of those cores, Linux gets some of those cores, Mac gets some of those cores. Some of the RAM is dedicated for Mac, so on and so forth. So a lot of times when you get to these machines that have huge amounts of RAM, huge amounts of cores on the processor, these are typically more server class machines, which are trying to do multiple things at the same time. All right. Where a majority of people, this kind of is where Best Buy gets you with gaming machines and stuff like that. You go and buy a computer from Best Buy, comes with 64 gigs of RAM, some kind of famous, 4090 Ti graphics card or something like that. The graphics card's important. You're going to be using that horsepower for your video games. But the RAM, I doubt you'll ever use even half of it. But it looks good on paper. So when you brag about your specs, it's that type of thing. All right. So in any case, right now we need a big enough number for hexadecimal, let's say, to represent those memory addresses. And if we say right now, even our biggest servers in the world have like 2 terabytes of RAM in them. Not hard drive space, RAM, which is like your fast memory. That talks directly to the CPU. Not the fastest memory in your computer, but it's faster than your hard drive, than your solid state drive. But even our biggest ones have 2 terabytes of memory, which means that if we represent locations in memory, if each house is 1 byte big, usually houses are bigger than that. Usually the way memory is represented like in a 64-bit operating system, they would be 8 bytes. So each house is like an 8-byte mansion as opposed to a 1-byte tiny home. Make sense? All right, so kind of connecting it back to real life, because I know we're just throwing numbers all over the place here. So if we think about this 2 terabyte long street, and each house on the street is an 8-byte mansion, 64-bit location. All right, that means they can they're uniquely addressed, and that's how much data can be stored in that one place. Now, if you want to build a bigger house, you just make sure, like if you're building a house in real life and you want to build a humongous compound, right? You're going to look for more acreage, right? But you don't look for 1 acre here and 3 more acres down the street and 6 more acres around the corner. You need all that acreage right next to each other, right? It's called contiguous memory. Same thing happens in computers. So if you want to build something bigger than 64 bits, you need to hold something bigger than 64 bits or 8 bytes in memory. Well, then you just need to find buckets of memory that are right next to each other, and you reserve that. You buy those plots of land and it gets reserved for your program, and now your stuff can live there. Okay, but in a worst case scenario, using a modern operating system that's typically a 64-bit operating system, 1 byte is 8 bits. So 64 bits is equal to 8 bytes. If we just assume we never use more than 8 bytes for any individual house on this street, that means we can take two, well, it's going to be too big of a number for it to show on here. So let me show you this, just so we can have everything in the right context here. Let's go right here. I don't know, let's just do, say, numbers, maybe, something like that. And we're going to create 2 columns here. All right, good enough. All right, so we've already talked about a bit. A bit is a 0 or a 1. All right, then we have something called a kilobit. Are you dying? Okay, a kilobit with a small b. Usually we will use a small b. Sometimes it's a small k, but when we say kilobit instead of kilobyte, there is a difference. Okay, we're going to talk about internet speed in a second, where they get you. All right, 1 kilobit is 1,024 bits. 1 megabit is 1,024 kilobits. 1 terabit, or sorry, 1 gigabit is 1,024 megabits. 1 terabit is 1,024 gigabits. All right. Now, why do we jump by 1,024 instead of 1,000? Because if you come from like a physics background or something like that, and you think about kilo and mega and giga and tera, you know, these different ways of kind of multiplying values, we usually think about going up by thousands, right? Why do we do 1,024? Go ahead. Most of the way there. It's a multiple 2, right? These are all powers of 2. 1,000 is not a power of 2. 1,024 is. All right. So why do we use 1,024 here? It's because computers make us, right? This is the compatible language for us to talk to computers. All right. Now, on the flip side, we have this thing called a byte. And a byte is 8 bits. We have a kilobyte, which is 1,024 bytes. We have a megabyte, which is 1,024 kilobytes. We have a gigabyte, which is 1,024 megabytes. We have a terabyte, which is 1,024. That's gigabytes. And we can keep going. We can say exabytes is the next one, and petabytes, and yada, yada, yada. Okay. So this is how we represent size of memory, or size or speed when it comes to technology. Okay, so we see that there's a pattern. As we move up and down each of these columns, it's a multiple of 1,024. If we jump from one column to the other, it's a multiple of 8. All right, so using this as an example, let's say internet speed. So this is where they get you. So this is going to be a similar question to what I asked about how much RAM is in your computer. So this is an additional assignment for Some of you, if you didn't know how much RAM is in your computer, you're going to go figure that out because you should know about, the equipment you use for work, right? We're going to all be technology workers. You should know what you're carrying around. You shouldn't have to, I don't know, have to go ask grandpa or something like that. So when you see commercials for like Spectrum Internet, cable modems or something like that, okay, they get you because almost always they say, oh, your internet speed is 200 meg internet. They just say meg. They don't tell you what the last part is. So anybody here know what your internet speed is at home? What do we got? 300 megabit. Okay. So when you saw the commercial for it or the advertisement, it probably said something like 300 meg internet. But when you actually look at when you see what the advertisement is, it's going to be Mbps, megabits per second. If you wanted to see the equivalent of this in bytes per second, you would take 300, you divide it by 8. So that is 37.5 megabytes per second. So when you download a file, the fastest he's ever going to see is theoretically 37.5 megabytes per second. He won't see this 300 number because that's not a byte, it's a bit. But it lets them say a bigger number, right?
Could I recap something?
Sure, go ahead.
Okay, so a byte is 8 bits and a bit is a single binary integer, right?
Single 0 or 1, yes.
Yeah, okay.
Now, some of the newer internet now, they're starting to sell gigabit and 2 gigabit internet, right? Or they might say, oh, you get 1 gig internet. All right. So if you go out and you get 1 gigabit per second internet, this is actually equal to how many megabytes per second? So first we got to turn gigabit into megabits. So 1024 times 1 is 1024. So this is equal to 1024 megabits per second. Which, if we divide that by 8, we get to megabytes per second, which is 128 megabytes per second. So gigabit internet gives you a theoretical download speed of 128 megabytes per second. Now, how often are you going to be actually downloading a file at 128 megabytes per second? Not very often. Every now and then, you might be able to get that kind of speed from certain sources. Okay, because keep in mind, just because you have a water pipe coming to your house, that's effectively what internet is, right? You have this giant pipe coming to your house that has the capability of carrying 128 megabits per second through that pipe before the pipe is filled. All right, you're still at the mercy of who you're downloading from. Now, most of your sources, when you go to a website, google.com or whatever website you're going to, okay, even though you have the capability of grabbing data from them in 128 megabytes per second in this example, if you have gigabit internet, if they can only put it out at 3 megabytes per second, that's all you're going to get. You're limited by how fast they can give it to you. Okay, does that mean that you're wasting your money when you buy gigabit internet for your house? If very, very, very few sources could ever give you data at that speed. Why do you think you might still need that speed internet? What's a rationale? Go ahead. Oh, go ahead. Yeah, go ahead.
Nowadays, like games are like 500 GB, and for esports players, they need kind of that speed.
Well, so now we talk about what does speed mean to an esports player. So if you're playing one of these games like Call of Duty, something like that, one of these esports games that's online, right? Is there actually a difference between gigabit internet and 200, he said he had 300 megabit per second internet. So if he's playing a game against somebody with gigabit internet, does that gigabit person have an advantage over him? Go ahead.
The neck of time you can say, or the different frame rate.
Yeah, the latency, the ping rate. So that max speed doesn't have any difference, right? The difference is how quickly, when he makes a move in his game, how quickly is that information propagated over the internet. Okay. When he updates his position of his character in the game, that's a little tiny piece of data, right? It's 32 bits of data or something like that. You don't need 128 megabyte pipe to send, 4 bytes of data. But you want that data to travel across the internet as fast as possible. It's not a lot of data, but you want it on a rocket ship, not on a horse and buggy. Make sense? So this goes back. So anybody here live out in the country where you have satellite-based internet? Oh, we got a fun one. Okay. Do you know what your internet speed is? Killing me. Okay. Chances are he probably has an internet speed that actually doesn't look that bad on paper. I bet you're probably getting something like 300 megabits per second. The difference is that latency, that speed. Okay. He would be terrible at online games. Okay. Because there's a big delay, right? Now, does that mean that he can't watch Netflix? No. He starts streaming. What does it do? It just takes a little bit longer for it to start. But once it gets enough of a lead, it keep up, right? It's the real-time stuff. So with satellite, you're traveling to space and then back down into this dish, right? And you're limited by the latency that guy can communicate with the internet. So it's not a maximum speed, but his ping is not up to snuff for gaming. Okay. So go ahead.
My internet speed says that it's 702/650. What does that mean?
Yeah, so that's upload versus download. So when you are downloading a file, let's say you're downloading a big game, like that was an example used here in class, you would be getting that first number, the larger number. So typically our modern internet connections are what are called asynchronous. The download speed is almost always faster than your upload speed. Now, what you just described, though, is actually a pretty fast upload speed given that download speed. So were you telling me what they advertise your internet to you for, or were you showing me were you telling me the result of like a speed test?
Nope, I'm actually reading what my specs are giving me in my settings.
Oh, interesting. Okay. Yeah, I mean, those numbers just seem closer than I would have expected them to be, but that doesn't mean it's impossible. So a lot of times, like gigabit internet might be gigabit down, and it might be like 300 megabit up. Okay, so when we use our upload on our computer, that might be our common use, is like attaching a file to an email or something like that, right? Okay, your uncommon use, common for some people, although I guess it's become more common even if you're not aware that it's happening, might be how many of you have ever used a tool called BitTorrent? Okay, a couple people have used it because they know about it. A couple people didn't want to admit that they use it. BitTorrent is not illegal, just happens to be used for like stealing movies and crap like that. But actually, most of the big companies now that do like software updates, whether it's Windows or Mac or any of your video games and stuff like that, they actually leverage a distributed technology like BitTorrent for distributing their updates. Okay, because like I said, let's say you're Microsoft. Now, does Microsoft probably have a pretty impressive upload on their connection to the internet? Sure, I'm sure it's higher than any of our individual uploads are. But is it infinite? No. And how many users does Microsoft have that's requiring downloading stuff from Microsoft? We'll round down and say a lot, right? Okay, so if everybody has their modern internet connections and everybody's expecting to download directly from Microsoft at maximum speed, Microsoft's going to run out of bandwidth very quickly. So what they've instead done is they release updates in kind of waves. So only some people get it. And then what ends up happening is when you get your update, you might be downloading part of it from some other user, not directly from Microsoft. So they distribute the network. to do it. So now we're getting into some what's under the hood networking type stuff. Not really part of the knowledge in this class, but again, we're trying to get to know this guy and you know the what the playing field looks like, right? So in any case, when we deal with these sizes, megabits, megabytes, gigabits, gigabytes, all sorts of things like that, that has meaning, and it should have meaning to us. All right, because when we, for instance, need to create a piece of data in our program and we're going to store it in memory, we want to have an appreciation for how much data can we actually store in memory. Make sense? All right. Now, we're going to see, well, here, let's just actually, we'll get ahead of it a little bit. How many of you have heard of the Y2K problem? Okay. What was the Y2K problem? So this was in the year 2000, so 24 years ago. How many of you were alive in 2000? Half of a person? One and a half people. All right. What was the Y2K problem? Go ahead.
Computer system running on the date, time, whatever it is, for a year, and then it's put you to 2000, and not being able to process that.
Okay, so the problem is that because of the way dates were stored, years were stored in computer programs up to that point, the year 1900 and the year 2000 looked the same because they used 2-digit years. Good. That's okay. All right, so we had two-digit years. So like 1998 would just be represented as 98. Make sense? So now when these people started writing programs using some older languages like C and C++, which we're going to use in here, you know, back then, memory was not that big. They had to purposely look at how can I shrink my data down to minimal use so I don't run out of RAM in my computer. Okay, so we use 2-digit years instead of 4-digit years. So what does that mean? To hold 2-digit years, we need to hold a number between 0 and 9 and another number between 0 and 9, right? How many bits does it take to hold a number between 0 and 9? What's the minimum number of bits that we can represent a 9 with? Well, a 7 takes 3 bits. 111 gets us to a 7. So really, we actually need 4 bits to represent all the values up to 9. And then we have some unused space in there, but 4 bits for one value. And then to get that second digit, it's another 4 bits, right? So we need 8 bits of, or 1 byte of memory in order to store a single 2-digit number. All right. So the people writing those programs back in the 60s and 70s, you know, they decided we are only going to use 1 byte of memory to store a year. Then we got to the year 2000, where in their mind, they're like, either that year will never come, because we're going to probably blow ourselves up with a nuclear bomb or something, or there'll be a replacement technology that whatever we're choosing today is going to be so antiquated that it doesn't matter later on. Well, that's not what happened. We roll into the year 2000, and all of a sudden we have all of these years stored as 2 digits. And the next morning, 1900 and 2000 means the same thing in these computer programs. So when they go and start sorting stuff, banks were going to break, electrical grids were going to break, all this stuff. I remember sitting on the couch, like now, you kind of maybe you stay up late enough to see the ball drop, right? I remember like sitting there on my couch just watching, they broadcast, when it hit midnight in each time zone. And you're just waiting for what, I don't even know what I was hoping for. Just you're waiting for the lights to go out or something. But everything leading up to that time, there was this giant movement in the computer software development world to upgrade all the software to use 4 digits instead of 2 digits. But understand that that original decision came from them deciding we are only going to dedicate 1 byte of data to store a year. When really to have 4-digit years, we need like to store it as 1900 and 2000. We're going to need 2 bytes of data. Make sense? Okay. So the Y2K problem was effectively that. So 4-digit years would take 2 bytes of data. So that is 4 bits per digit 0 to 9. That's how that math works out. Again, this isn't something I'm going to directly test you on, all these little nuances of this stuff, but I want you to kind of take it all in and kind of see where all this stuff fits in the playing field of working with these computers. Okay. Now, having said that, we have to go back to that decision making from the 1960s and 1970s, because that's the language we're going to use in this course. We're going to use C to begin with and C++ pretty quickly after that. We'll talk about that here in a few minutes. But these are languages that have not been fully replaced, but there are newer languages that have, you can kind of think of them as more modern technology that have some conveniences built into them. Quality of life type things. Not that these old languages don't still work. All right. So this is always a fun one. So we're going to say 1996. Let's say 1996 memory. In 1996, I had a computer that had 8 megabytes of memory in it. And that was considered pretty beefy. It's probably equivalent to 64 gigs of RAM today. Equivalent, bragging rights type thing. All right. Now keep in mind, 8 megabytes of RAM is equal to how many gigabytes? If we want to put that into our mindset today. So that's 8 divided by 1024. So that is 0.0078 gigabytes. 0.0078 gigabytes. All right. So my computer right here has 96 gigabytes of RAM. So 96 divided by 0.00, what was it? 76, whatever. 78. All right. What is that? What is that number? So I have 12,307 times more RAM in this computer than I did in 1996. All right. So that's not surprising. We assume that as time goes on, your internet speed has gotten faster and faster and faster. Way back when, before you were alive, we had dial-up internet. At the very least, you've heard of it, right? Any of you ever used dial-up internet before? Maybe you've seen it in a movie with all the like. The early days of the internet. So those were fun. And at some point, maybe we'll talk about what all that beeping is about. But in any case, so my computer had 0.0078 gigabytes of RAM back then. Probably we would have said 8 megabytes because that was considered impressive then. So I wanted to upgrade it to 16 megabytes of RAM. So I needed to add an 8 megabyte chip. Now, has anybody purchased RAM for their computer recently? What's the cost of RAM? $40 for how much? Okay, so 32 gigs of pretty modern RAM. Okay, so 32 gigabytes. So in 2024, we're going to say 32 gigabytes of RAM is, you want to say $45? That roughly, we're in the ballpark. All right. So that means that a gigabyte of RAM today. So we take 45 divided by 32, it's $1.40 per gig. So dollar per gigabyte today. So how many megabytes are there in a gigabyte? 1024. Okay. So if I take $1.40, divide it by 1024, and then I multiply that by 8. That gets me the cost for 8 megabytes. So the cost of an 8 megabyte chip today is a penny. Yeah, 0.01, a penny. Which is 1 cent for 8 megabytes of RAM today. So now the question is, 1996, how much did 8 megabytes of RAM cost? It would cost you a penny today. What do you think it cost in 1996? Any guesses? Just throw some out there. What do you think? Good. $5. Okay. Way more than $5. Go ahead. More than $200. It was $1,000. 8 megabytes of RAM was $1,000. How many of you think that's ridiculous? All of you should, right? That's after the price of RAM had already come way down. It used to be even more expensive. This is in 1996. We're talking about with that Y2K problem, the rationale that programmers went through in the 60s. 8 megabytes of RAM didn't exist in the 60s. That would be like saying, just hand me Fort Knox or something like that. But the equivalent amount of RAM in the 60s, if you could piece it all together, would have been millions and millions of dollars. Make sense? So it shouldn't be surprising that in the 60s, they made the decision of, hey, RAM isn't just growing on trees here. So we're gonna represent years using 2 digits instead of 4 because that's a significant price difference. Make sense? Good.
Due to the laws of supply and demand, the prices went lower, as time went on, or?
Well, I mean, a combination of a lot of things. So certainly, we've all experienced it when a new technology comes out. It's initially very expensive, and then it comes down in price over time as they're able to figure out how to mass produce it. So part of it is production. The other part of it is also just the invention of new technologies, the ability to fit more stuff in the same space. So for computer stuff, it ultimately comes down to like transistors. We keep coming up with better and better and better technology for fitting more and more transistors in the same footprint. If any of you have built a computer recently, so I'm guessing maybe you, since you bought some RAM, okay, do you know what nanometer technology your CPU uses? Okay, but you know what I'm talking about. When something when a new technology, a new architecture comes out, it usually says based on something NM. You've seen what I'm talking about? Anybody know what that means? When something is based on 5 nanometer technology versus 10 nanometer technology versus 20 nanometer technology. Go ahead. Yeah. You can think of it as kind of the space between wires before they start interfering with each other. So over the time, we've gotten better and better and better at, we've created machines that are able to do printed circuit boards. That's how our stuff works today. You don't have some dude in a warehouse with a soldering iron with a giant monocle just ripping things away at 5 nanometers, right? That's not happening. Okay, but we have modern technology that allows these machines to print these circuit boards where these wires are at the atomic level, basically on top of each other. Make sense? And every year that number keeps going down. Right? I mean, it used to be impressive when it was like 30 nanometers. Like that seemed ridiculous. Now I think the Apple's latest thing is a 3 nanometer process. I mean, it's stupid. Okay, but you know what? If we fast forward 5 years, 3 nanometers is going to seem like it's like a this giant. Like, how did we ever survive? You couldn't have worked with that. All right, so part of it is back then in the 60s, could they have made 8 megabytes of RAM? Sure, but it maybe would have taken a football field for the space, and I might be underestimating. I'm just kind of throwing an example out there, right? Okay. You've all seen, and if you haven't yet, you'll see it in your 175 class, like the history of computers. When some of our computers used to take up gymnasiums, like UNIVAC and EDVAC, these early computers before the transistors. These guys had vacuum tubes. So basically a light bulb on and off, right? So you needed physical space. For an 8-bit number, you had to have enough physical space for 8 light bulbs. A light bulb is a transistor in that example. Makes some sense? Okay, so that means that a 4-digit year would take 16 light bulbs to represent that. To represent one 4-digit year, 16 light bulbs. Now, do you think modern computers, when you go to like Amazon or something like that, and they're storing all these dates and stuff, do you think they're only storing one 4-digit year? Or are they storing, we'll round down and say a bazillion 4-digit years? A lot of light bulbs, okay? And even when we turn them into transistors, it's still a lot of transistors. So our technology allowed us to fit more and more transistors into smaller places. We got better and better and better at mass producing these things, which then dropped the price way down, okay, to where it is today. And if we fast forward 10 years, the price of, the equivalent of 32 gigs of RAM is going to be even less. I bet you in 5 years, 32 gigs of RAM will be $15, something like that. But 32 gigs of RAM will no longer necessarily be as impressive as it is today. The 32 gigs of RAM in 5 years would probably be kind of like 8 gigs of RAM today. Something like that. All right, so it's all a moving target. All right, but in this case, when we're talking about bits and bytes and all this stuff, we're talking about the amount of space that something takes to fit into. Okay, kind of like a shoe size. All right, make some sense? All right, so we can appreciate back in the 1960s, 1970s, that we had to really consider how much space we used to store something, because memory was really expensive. And even if you had enough memory, buying extra was really, really expensive or impossible, right? So it was in your best interest as a programmer back then to really sit there and think before you store some number, how big is that number ever going to get? Because I want to store it in the smallest footprint possible. Make some sense? Okay. Now we just went through this exercise and saw that the cost per gigabyte today is cheap, right? And a gigabyte can hold a lot of 4-digit. We said 2 bytes is what's required to hold a 4-digit year. So 1 gigabyte of memory. So a gigabyte is 1,024 megabytes times 1,024 kilobytes times 1,024 bytes. And we need to divide that by, well, we need 2 bytes for a 4-digit year. So we need to divide that by 16. So that means we can store 67,108 4-digit years inside of 1 gigabyte. But he told me that he has 32 of those for the $40. So we can store 2.147 billion 4-digit years and 32 gigs of RAM. It's a lot of 4-digit years. Make sense? So that's kind of the moving target we're dealing with here. In the 60s, we cared about this stuff. Today, as programmers, we want to appreciate it but we're much more lackadaisical about it, right? Today, if I'm going to store a number in a computer, I'm probably going to just throw it in something called an int. Okay, and we'll talk about that here, actually, probably here in a few minutes. Where an int in most programming languages is 32 bits, 4 bytes. Now, most of the time, the number I'm storing in there doesn't require anywhere near 4 bytes of data. But I just figure, I'm not going to waste my time min-maxing my RAM. I'll just, it'll fit in 4 bytes. If it doesn't fit there, I'll just go to the next guy up, which is a long. That's 64 bytes. And if that doesn't work, I'll just jump over to some object type that can hold even more. Okay, so we're not overly concerned today. We just make sure the bucket's large enough. We don't try to make it just a perfect fit anymore because we're lazy. But at the very least, as modern day computer scientists, we want to appreciate where some of these decisions came from. All right. All right. So now let's start getting over to our languages. So how do human beings solve problems? So one of the things we talked about the very first day of class is the idea that the reason that programming is hard is because human beings are really, really, really good problem solvers, yet we have trouble articulating to a computer how we solve a problem. So often we just do it and don't even think about it. I used the example of how many of you were coming to class and you weren't even paying attention in front of you. You were checking your email, whatever, bobbing and weaving in and out of people. So even walking through crowds of people didn't even require 5% of your attention. It was a background process as you were making your way to class. Okay. So but yet you didn't think about you shifting your weight from one foot to another, firing one muscle and another muscle. These are all things that were out of sight, out of mind. You didn't even have to deal with, right? That's how good of problem solvers we are. So it would be very difficult for us to, at any sort of, detail, tell somebody how we walked from our car to class or our dorm room to class, whatever it is, with a lot of detail. That would be impossible for us, right? We don't think in that level of detail. Computers require it. So right off the bat, we have to say, well, we already know that there's going to be a limitation for the types of problems we can even begin to articulate to a computer how to solve, because we really can't get to that level of detail ourselves. So right off the bat, we can start off with this idea that, hey, you know what? The problems we're asking our computers to solve are trivial problems compared to what a human being solves on a daily basis that isn't even worth our full attention. Make sense? So when you see these latest, greatest video games with all these explosions and all these things, whatever, high-end graphics, to write that game is orders of magnitude simpler than you walking to class in terms of the problem you're solving. All right. Human beings are really, really good problem solvers, but we don't pay enough attention to how we solve these problems anymore to be able to articulate how we solve them, which is the skill we need to tell a computer what to do. So what we try to do is we try to abstract how human beings solve problems. I try to get it down to these 3 steps. All right. So imagine if any one of these things was missing. So the first thing we do is we have to remember things. Now, I know some movies make fun of this, right? Where somebody has like short-term memory loss, right? So somebody walks into the room, says, hey, hi, I'm Mike. And like 3 seconds later, the person forgets they ever met you. That's been in various movies, and I'm sure it truly exists in real life as well. Imagine how debilitating that is, not having memory. That'd be rough, right? Okay, so we use our memory. We remember things. Now, you might think, hey, I don't have a great memory, but by most measurements, you have an amazing memory. You just might not have the memory that as good as somebody else might have. But you remember a lot of things. Like how many of you forget your name? Forget your phone number? Forget your age? That which does happen, actually. The older you get, you start forgetting your age. You got to like do the math. Okay. But you get what I'm saying. I remember my childhood address. I remember my childhood phone number. We haven't been in that house in decades. Okay. So, but these are things that are stuck in there for some reason, right? So in any case, human beings use our memory. We also ask a lot of questions. So what if we could remember things, but we didn't have a way of articulating a question to make decisions? You know, like when you leave the house in the morning, if it is cold outside, you might put a jacket on or a coat on, whatever it is, right? That requires several question and answers to determine what's the appropriate clothing to wear for the current weather. Make some sense? So asking questions is an important part of how human beings solve problems. We also do a lot of repetition. Once we have a process for something, we repeat it over and over and over and over again. Walking to class. You have figured out over the years how to walk, and walking requires a certain ninja move when you're on the left foot and another ninja move when you're on the right foot, and you just put those things back to back and repeat it over and over and over again, and you somehow avoid falling on your way to class most of the time. All right, depending on how late you were out the night before and you know, what sort of non-allowed materials you had on campus. All right, so punchline here is that what I'm telling you is that 100% of programming languages have facilities for these three things. All right. Remember back to day one of class, I said something along the lines of programming is the skill set, the language doesn't matter. Programming is like a sport. You got to put in the reps. The language that you're using does not matter. All right. Because all programming languages have facilities for these things. What you're really training yourself to do is how do you think and solve problems in terms of telling this thing what to do, as opposed to the way you can solve problems as a human being, which allows you to skip a whole bunch of steps because humans are pretty good at gluing, kind of, you know, dealing with big picture things and just kind of figuring it out as we go. Computers can't do that so well. We're starting to move in that direction with AI, kind of creating a mesh that sits between us and the computer where maybe we don't have to explain stuff at that level of granularity because we can let the AI effectively map it to instructions on the CPU, but we're not quite there yet. All right. Okay. But what I'm telling you is every single computer programming language, any one you pick out of the hat, Java, C#, C++, Python, go down your list. Every single one of them will have facilities for remembering things, for asking questions, and for doing repetition. So if you already know programming, if you already know how to conceptualize a problem and explain to this guy using some programming language to solve that problem, you can pick up another programming language conveniently because all you have to do is ask yourself, well, how do I remember things? How do I ask questions? And how do I do repetition in this language? What's the syntax for those three things? And once you know that, you can solve a huge amount of problems with that language instantly. So I would say programming is difficult initially to learn your first language. But once you know how to program, you will be able to pick up other languages in a weekend. And really, you'll be able to pick them up in 20 minutes to be able to function enough with that language. And we're going to prove that through the next several courses, because I mentioned in here, we start off with C, we'll roll into C++. From there, we'll roll into Java. So you're actually going to hit 3 different languages in this class. Okay? And just when you think you're comfortable with one, I'm changing it on you. Okay? But you'll realize they actually are all the same because they all come from C. But you know, the bottom line is I'm going to attempt to prove the point to you by continually pulling the rug out from underneath you. And when you're done with your first 2 classes, you're going to know C, C++, Java, C#, Unity game engine. You'll have 5 different programming tools under your belt after 1 year of programming. It's pretty solid. Any one of you can go and get a job professionally after you know those 5 languages. All right. So my next slide is this thing called the mapping. So I mentioned all programming languages have facilities for these 3 things. Typically, remembering things is done through something called variables. Asking questions is something done through some conditionals. Usually they're if statements. if this, then do this, otherwise do something else. And then we have the ability to repeat patterns. We do this through loops and we do this through functions. All right. So 100% of languages have these things. All right. So let's start talking about some programming stuff now. So the next couple of slides deal with looking at programming languages from several different angles. So one thing we might say is, oh, there's two kinds of programming languages. We have loosely typed languages and we have strongly typed languages. Well, what does that mean? Because being able to look at a brand new language you're trying to learn and being able to identify which kind of bucket that language falls into will give you a lot of information about how you can wield that language. All right. A loosely typed language. So we're going to say this deals with defining variables in a programming language. Ooh. A loosely typed language, we create variables. Catch up. Without having to tell the computer what kind of value we intend to store in that variable. Whereas a strongly typed language, we create variables being required to tell the computer what kind of value we intend to store in that variable. So let's look at a real life example of this. So we're going to go out to Target. We're going to buy a big Tupperware thing, big box that you're going to keep under. You're going to store stuff in it, keep it under the bed. All right. The loosely typed version of that would mean you have this box, you put no label on it or anything, and you put, let's say you put in your tax documents in it. And then 3 years from now, you pull it out and you say, okay, well, I don't care about this old stuff. So you throw those out and then you throw shoes into that thing. Is that allowed? You got a container, shoes fit, tax documents fit, no harm, no foul, right? Okay, that would be loosely typed. You have a container that can remember stuff, that can hold stuff, yet you can put whatever kind of thing that would fit in that container. Alternatively, a strongly typed language means when you bought that Tupperware, okay, you put a sticker on it that said taxes. Okay, and from that day forward, you made a blood oath that you will never put anything but taxes into that container. All right. So several years later, you pull that container out, you decide, oh, I'm going to get rid of these taxes. I want to store shoes. That's no longer an option. You have to look at that and say, oh, what could have been, right? Now you got to go back to Target, spend another $12 on a container to put your shoes on, and then you put the empty, sad tax container over to the side because you're done using it. Make sense? That's strongly typed language. Which sounds better to you? And I am tricking you. Does one necessarily seem way better? Human fairness might say, oh, well, feels like flexibility is kind of a good thing, right? You know, as long as there's not a significant price difference between the flexible container and the dedicated container, maybe you get the flexible one because it allows you to get more use out of it over time, right? Go ahead.
You need both.
Okay, tell me about that.
In some circumstances, you would need one or the other, but you would just, I mean, you might never know which one you're gonna need, so it's better to have both in the long run, just in case.
Well, what if they're both the same size? We have two 5-gallon buckets. One of them is labeled as can only store taxes. The other one is labeled as free for all, but they're the same size bucket. They just happen to play by different rules. Okay. Human beings might say, okay, well, I might as well have the flexible one as long as it didn't cost me that much more, right? You probably wouldn't pay a huge premium for that because at some point in time, if you're going to switch up what you're storing, you would just go buy a new one and save money in the long run, right? Okay. But presumably, maybe the more flexible one costs us more money, and that's where we have to make that decision. And that's where maybe the it depends thing comes in. Okay. When we're talking about programming languages, we have to change our mindset of what does it mean to cost something. All right. We're no longer caring about money. Now we might be caring about computing resources. We might be caring about speed. We might be caring about the memory usage, things like that. All right. So a loosely typed language is typically slower because we have to have what's called a type inference engine constantly running that figures out what kind of value is stored in a variable to police how we are able to use it. So for example, let's say we have a variable that's in a loosely typed language. So we didn't have to speculate. We didn't have to state what kind of value we're going to store in here. This is our flexible container we bought from Target, okay? And originally we put a number in there that we intend to do math with, okay? But we don't have to label it. So that means whenever we go to use that storage location, this type inference engine peeks in there. So let's say I'm gonna try to add 10 to whatever it is. I'm gonna do some math for whatever reason. I want to add 10 to whatever's in that container, whatever's in that variable. That type inference engine has to say, hold on a second, let me peek in there and make sure that is a mathable thing. All right. It looks in there and says, okay, there's a number in there. You can add 10 to it. We're good to go. You have to check. All right. But we always have to check because since that was loosely typed, nothing prevents us from taking that number out of there and tossing an ice cream cone in, right? And all of a sudden, next time around, your program says, hey, we're going to add 10 to what's in that container. Type inference engine leads over, looks at the eyes. There is melted ice cream in that thing. Okay, adding 10 to it does not make any sense, right? Okay. That type inference engine is constantly being this extra double checking thing, which takes time. Make sense? So now the question is that always bad? Because now, just in one or two sentences, we've gone from, oh, well, flexibility seems like the way we should go, to all of a sudden, yeah, we don't want to be flexible ever. You know, we don't want to have double checking thing. If that had a number to go in there to begin with, that is what it will die with, is numbers in that thing. It makes sense? Okay. But I'm telling you that programming languages fit into both these categories. How many of you have heard of Python? Very, very, very popular language today. Mostly among, let's call it, non-dedicated programmers, but we'll get into that more. But Python is a loosely typed language. So you can create a variable in Python and throw a number in it 1 second, and 3 lines later, toss an ice cream cone in there, which would be an instance of an object. We'll get to that at some point. That's a programming joke, maybe. So certainly these languages are popular. I just gave you a modern example of one that exists. All right. So loosely typed languages tend to be slower, but guess what? Just like we've already talked about today, computers are really fast. Now, a majority of the programs we might write for telling computers what to do, a human being is not going to be able to tell the difference between a loosely typed language and a strongly typed language during runtime. It's going to happen so fast that it's going to feel instantaneous to us. Only in certain applications does ultimate speed really matter, right? Maybe it's in video games, for example, especially since now we have like esports and things like that where, hey, there is a lot of stuff going on here, and the faster we can make it, the fewer double checkings we have to do, the better off we're going to be. Same thing's true maybe with let's say the software that controls the airbags in your car. Okay. You probably want that to make the decision of whether to deploy that airbag as fast as possible. We don't want somebody checking for ice cream cones, right? So it's not that one is better or worse than the other. There are times for both. But generally speaking, I'm just going to make up a number. Let's call it 90% of the time. A loosely typed language will feel just as fast to the end user as a strongly typed language. But it is something for us to consider. Again, this is knowledge of the programming language under the hood, so that when we're learning a new language or when we're determining what language should we use to write this tool, we have to first ask ourselves, well, does it need to be really, really fast? Does it need to be as fast as possible? If the answer to that is a critical yes, then any loosely typed language gets thrown out the door. We're not going to use that because we need to be fast. All right. We just need it to feel fast enough. Everything's a free-for-all. In fact, you probably lean towards loosely typed languages unless something else disqualifies it. All right. So strongly type, we're going to say typically faster, since a variable will always hold the type of value it was originally built to hold. No double check. All right, questions about that? Now, as we go through all these things, what I want you to keep doing is trying to connect this back to your experience as a human being. That's why I'm using normal human examples like Tupperware and storing taxes and storing shoes, because it's all the same stuff, because we invented the programming languages. And we invented programming languages to help us solve problems, help us tell a computer what to do. And guess what? We decided, you know what? We already think like people. So we just need a tool that allows us to use our current problem solving to tell this guy what to do. So almost every example in computer science is going to be an abstraction of how humans already solve problems, how you already know how to solve problems. And we get in our own way. Gets back to like the big memory addresses. We don't blink, we don't bat an eye at our very complex human addresses, 123 Elm Street, Grafton, Wisconsin, 53024, right? We don't bat an eye out of that because we've seen it for forever. Yet, the second we glance at a hexadecimal number listing house 2472, we freak out. It looks scary when it's so much simpler. Make some sense? All right. Notice this guy has the same title. Two kinds of programming languages. Looking at it from another angle. We have interpreted and we have compiled languages. Interpreted languages use a piece of software, usually called an interpreter, during runtime to convert the logic of the program into usable logic on that computer's hardware. So real life example of this is, let's say that the let's say the president of Thailand is given some speech, and the speech is given in Thai. And does anybody in here speak Thai? Let's just assume we don't. There is anybody, break my example, but most of us don't speak Thai. We're all interested in what this speech is all about, right? So are we just out of luck, or might we get an interpreter who comes and, maybe he's 1 second behind the Thai person and they're saying it to us in English. They're translating it for us. They're interpreting it for us, right? Do we still get the words? We still get the idea? Sure. With a little bit of a delay? Sure. So interpreted tends to be a little slower because there is an extra step between running the program and it actually executing on the computer's hardware. Make sense? Now, is this always a problem? Or are we right back to what we said before? Computers are really, really, really fast. So most of the time, that translation is going to happen so quickly, we're never going to notice. Python, for example, is an interpreted language, the loosely typed interpreted programming language. Compiled languages use a piece of software it's called a compiler prior to runtime to convert the logic. Actually, I'm going to say to convert the high level programming language syntax. We talked about high level, low level, and machine language last time. High level has a one-to-many relationship with the CPU. Low level has a one-to-one relationship with the CPU. Every line of code translates into exactly one magic trick the CPU knows how to do. Okay. Whereas machine language is us there just spitting out zeros and ones. Definitely don't like that one. Barely tolerate the low level. We're pretty cool with the high level. All right. We're going to complain about it because we're people and we like to complain, but high level is where we're going to live for right now. Although now we're getting into some of the AI stuff, and I'll actually show you some examples of this as we get into it, because it's a cool problem solving thing. But I'd really encourage you not to take advantage of this. So for instance, once you become a good enough programmer that you pretty much, you can look at a problem and you take that time to kind of draw out your plans. How am I going to solve this problem before you just jump into the code? Because most of you, what you're going to want to do is just jump into the code right away. And then after you get 4,000 errors, then that's going to scare you away a little bit. You're going to come to me and say, oh, I suck at programming. I'm never going to get this. Everybody else in the class seems so good, blah, blah, blah. Keep in mind, most of the people who talk in class are people who've probably programmed before. The rest of you think you suck at programming and don't want to embarrass yourself, so you just don't say anything, right? When 98% of the people in here are beginners at programming, and you're running into the same headaches and the same nightmares as everybody else. The rest of the people maybe are getting overconfident, and when they get to the second or third class is when the train finally hits them, right? I mean, I guess it's possible they've been programming for a long, long, long time, and this is a snooze fest for them, throughout the entire undergrad. But at some point, they're going to hit a wall where this is no longer easy stuff they've been doing for years. So if it were me, I'd rather be a complete beginner, not having any bad habits, and learning programming from obviously an amazing professor. Okay. And then you'll go and become an awesome programmer, go and make your zillions of dollars and never have to worry about it again because you already know everything about programming. Okay. Because I've taught you everything I know. Okay. Which has, I guess, been enough up to this point. All right. So we like the high level languages. We appreciate those low level languages. We saw the hello world last time in assembly. Okay. We definitely don't want the zeros and ones, but we're happy to beat the computer up. All right. So compile languages use something called a compiler. What's a compiler? A software tool that converts between a high level language and a low level language. All compiled languages will use a compiler where you write your high level code like C, C++, Java. All those are compiled languages, by the way. Java is actually a little bit of a weird guy. He's sort of compiled and sort of interpreted at the same time. Let's put a pin in that, and we'll talk about that when I convert us over to Java. It's mostly a compiled language. Because remember, Java is kind of this upgrade to C++. Comes with some good, comes with some poor assumptions. Microsoft still tried to steal it, blah, blah, blah. So anyways, all compiled languages will use this compiler. It's a piece of software that you run it through before you try to run your program. It will convert your C, C++ code into assembly code for this operating system and this architecture. Talked about that last time, right? That we are targeting an architecture as well as a operating system. Because we saw last time that Hello World program utilized the system calls of Linux as well as the assembly language that Intel processors speak. We were able to put both of those things together to talk to this computer in a most human way possible. Okay. But that's not something a human being wants to sit there and do. You don't write your whole program out in C++ and then sit down and says, okay, well, now I need to transcribe this to assembly. Okay. No, you don't want to do that. You're going to let some program do that for you. Sure. A human being had to write that program before. Not your problem. Okay. Today, as modern day computer scientists, we can just appreciate that somebody else wrote that, right? So that's what a compiler does. Takes our C++, turns it into assembly code. The last tool here that I'll introduce just as our last piece here, for those of you who have coded before, you may have heard of something called a linker. All right. So the steps that happen when you compile a program is you first run it through a compiler, takes your C++, converts it to assembly, and then we link it, which turns it into an executable on that operating system. Something you could double click on and it runs. Converts compiled code into an executable file, bringing all the extra libraries that might need to be involved into this one little package, and then you double click on it, your program runs. Bringing all the libraries together.
You're writing this down in notes, right?
It's in the presentation. I keep hitting save after I type every little thing. So if you just have the presentation open on your computer from Blackboard, you'll see these things updating in real time.
So you're not screen sharing? You didn't intend to?
Oh, that is an amazing thing that I can't believe we spent an hour and 15 minutes and nobody said that to me. I am not.
I'm sorry.
It's fine. Well, so this particular lecture is going to require you to sit there with the slides in front of you. So it is all recorded. So you'll have, let's see, will you have my screen? I'll have to look. You might have my screen since I did record it, even though I didn't share it. I'll have to look, but you'll have my words and you have the updated presentation.
Okay, cool.
So in the future, if you don't see me sharing my screen, scream at me. I must have focused too much on hitting record, which I definitely did do, and forgot to share my screen. I apologize.
Yeah, no, I probably should have said something about it earlier.
All right, so I'll stop.